Good morning, students. In the last period, we have discussed about the qualitative properties. In that, lowering of vapor pressure, depression of boiling point. Now, today, we'll say about the depression in freezing point. In the last period, we have discussed about the elevation of boiling point and the lowering of vapor pressure. Now, the depression in freezing point. Before knowing the depression, we must know what's meant by the freezing point. The freezing point of a liquid is the temperature at which the liquid and the solid are in equilibrium, and the two phases have the same vapor pressure. किंवा आपण साध्या सोप्या भाषेमध्ये आपण कॉमनली असं म्हणू शकतो किंवा ज्या टेम्परेचर there is a change of phase from liquid to solid. Means the liquid, the freezing point of the liquid is the temperature at which the liquid and the solid are in the equilibrium, and the two phases have the same vapor pressure. That temperature is the freezing point of the liquid. The general experimental observations is that the freezing point of the solvent is lower by dissolving the non-volatile solid into the pure solvent. Thus, the freezing point of the solution containing a non-volatile solid is lower than that of the pure solvent. म्हणजे जसं आपण बॉइलिंग पॉइंट एलिव्हेशन मध्ये पाहिलं, प्युअर सॉल्व्हंटचा बॉइलिंग पॉइंट आणि when the non-volatile solid is added into that pure solvent, the solution, the boiling point of that solution increases, while the boiling point of the pure solvent is less as compared to the boiling point of the solution in which the non-volatile solid is added. Similarly, like that way, when the pure solvent is freezes, the freezing point of the pure solvent is greater than the freezing point. The freezing point of the solution containing a non-volatile solid is lower than that of the pure solvent. Pure solvent, so for example, pure solvents are on the freezing point upon the pyra. For example, it may be the 30 degrees Celsius. When the non-volatile solid is added, into this solvent, at that time this freezing point decreases. Suppose that it will be the 30 degrees Celsius. There is a difference between the freezing point of the pure solvent and the freezing point of the solvent in which the non-volatile solid is added. If you can take the freezing point. T1 naught is the freezing point of the pure solvent. T1 naught is the freezing point of the pure solvent. And TF naught, sorry. And the TF is the freezing point of the solution in which the non-volatile solute is added. At that time, we can say that the TF naught is greater than the TF, because the freezing point of the solution in which the non-volatile solute is added, its freezing point, how much? It is TF. While the pure solvent of the freezing point of the pure solvent, that is TF naught. And when the non-volatile solute is added into that solution, at that time the freezing point will be decreased. That is, suppose that it is considered as the TF. Then the TF naught is greater than the TF. The difference between the freezing point of the pure solvent and the solution in which the non-volatile solute is added, that is called as the depression in freezing. That means the delta TF, the change in the freezing point, what it is? The delta TF naught minus TF. Delta TF क्या है ना? Depression in freezing point. Depression in freezing point, that is delta TF is equal to T naught F minus TF. Suppose this is the one equation. The effect of the solution, effect of the depression in the consequences of a vapor pressure lowering, the effect of the dissolution of the non-volatile solute can be understood in terms of the vapor pressure lowering. Suppose that this graph is plotted in terms of the temperature and the vapor pressure. At that time, you can say that consider the vapor pressure temperature diagram. That is the vapor pressure temperature diagram. The diagram consists of the three curves. The AB is the vapor pressure curve of the solid solvent. A to B is the vapor pressure curve of the solid solvent. Then CD is the vapor pressure curve of the liquid solvent. That is the CD is the vapor pressure curve. This CD is the vapor pressure curve of the liquid solvent. And EF is the vapor pressure curve of the solution. EF is the vapor pressure curve of the solution that always lies below the pure solvent. Pure solventचा हा vapor pressure curve च्या खालच्या बाजूनच हा सोल्युशनचा vapor pressure curve आपल्याला आढळून येत असतो. It is important to note that the solute does not dissolve into the solid solvent. Solid solvent मध्ये solute dissolve होईल का? नाही. The curves AB and CD increases. AB and CD increases. Intersect at the point. Sorry, not increases. Intersect at the point B, where solid and the liquid phases of the pure solvent are in equilibrium, and the two phases have the same vapor pressure at the B. म्हणजे this AB and the CD, these are the two curves where they intersect at the B. And in that state, the temperature corresponding to the B is freezing point of the solvent. म्हणजे या ठिकाणी असणारे जे काही टेम्परेचर जे असेल ते टेम्परेचर काय असेल हो त्याचा फ्रीजिंग पॉइंट हा त्या सॉल्व्हंटचा आपल्याला आढळून येत असतो. Similarly, the point of intersection of EF, EF, the point of intersection. At that time, EF and AB, the solvent and the solution are in equilibrium and they have the same vapor pressure at the temperature corresponding to E is the freezing point of the solution. म्हणजे या ठिकाणी असणारे जे काही टेम्परेचर जे आहे या E या पॉइंट वरती ते टेम्परेचर फ्रीजिंग पॉइंट हे कशाचं असेल या सोल्युशनचं असेल. It is clear from this figure that is the freezing point of the solution TF is lower than that of the pure solvent TF naught. म्हणजे याच्यावरून आपल्याला हे लक्षात येते की फ्रीजिंग पॉइंट हा सोल्युशनचा फ्रीजिंग पॉइंट जो आहे तो प्युअर सॉल्व्हंटच्या फ्रीजिंग पॉइंटच्या तुलनेमध्ये हा कमी असलेला आपल्याला आढळून येतो. म्हणजे डिप्रेशन इन फ्रीजिंग पॉइंट दॅट इज द डेल्टा TF इज इक्वल टू TF नॉट मायनस TF. Here it is why freezing point of the solvent is lower by dissolving the non-volatile solid into the solution. At the freezing point of pure liquid, the attractive forces among the molecules are large enough to cause the change of phase from the liquid to solid. In a solution, the solvent molecules are separated from each other because of the solid molecules, and these separation of the solvent molecules in solution is more than in the pure solvent, and this results in the decrease in the attractive forces between the solvent and the solvent molecules. Consequently, and the temperature of the solution is lower below the freezing point of the solvent to cause the phase change. म्हणजे हे जे फ्रीजिंग पॉइंट जो आहे हा when non-volatile solid is added into the pure solvent, at that time it will be decreased. कारण का त्याच्यामध्ये त्या प्युअर मॉलिक्युल्स मध्ये प्युअर सॉल्व्हंट मध्ये असणारे जे काही मॉलिक्युल्स जे आहेत त्यांच्यामध्ये असणारा फोर्स ऑफ अट्रॅक्शन जे आहे ते स्ट्रॉंगर. बट when non-volatile solid it will be added into that solution, at that time the forces of attraction between the molecules will becomes weaker and it will be freezes suddenly. Hence that the freezing point of the solution in which the non-volatile solid is, it's low, it decreases. Now the concentration, freezing point, depression and the concentration of the solid. It is experimentally verified that for dilute solutions the freezing point depression, that is delta TF, is directly proportional to the molarity. Ha delta TF is directly proportional to molarity, where delta TF is equal to the KF into F, and the proportionality, where KF is the proportionality constant. If F is equal to 1 and delta TF is equal to KF, the cryoscopic constant thus is the depletion constant in the freezing point is produced by 1 molar of solution of the non-volatiles. म्हणजे ज्यावेळेस मोलॅरिटी जे आहे हे 1 असेल आणि डेल्टा TF हे is equal to the KF, at that time this solution will be the 1 molar solution. Hence, then what is the molar mass? The relation between molar mass of the solid from the freezing point depression. आता freezing point depression आणि molar mass यांच्यामध्ये असणारे जे काही रिलेशन जे आहे ते रिलेशन आपल्याला या ठिकाणी पाहायचे. The molar mass of the solid from molar mass of solid from the freezing point depression In this case, from the above equations that we have seen, that is the delta TF is equal to delta TF is equal to KF. हे जी आपण कॉन्सन्ट्रेशन आणि डिप्रेशन इन फ्रीजिंग पॉइंट यांच्यामधलं रिलेशन आपण जे पाहिलं, that is it is depletion in freezing point is directly proportional to molarity. From that we can take this equation, that is delta TF is equal to K of m, and the molarity of the solution is given by the formula, that is m is equal to molarity m. काय फॉर्म्युला आहे त्याचा? that will be 1000 W2 upon the M2 W. This is the formula of the molarity. Then putting this value into this equation. आता या ठिकाणी from this equation, the equation काय आहे? delta TF is equal to KF M, म्हणजे delta TF is equal to KF या m च्या ऐवजी काय 1000 W2 upon M2 W1. हे आपल्याला इक्वेशन भेटले. And from that the M2 is equal, मग याच्यावरून आपल्याला M2 हे भेटले. M2 is equal KF 1000 KF 1000 KF W2 divided by delta TF W. This is the molarity, molar mass equation with the from the freezing point of the depression. म्हणजे साधा आणि सोपा हे इक्वेशन्स आहे. First of all, we must know what is by the freezing point, then the freezing point of the pure solvent and the freezing point of the solution in which the non-volatile solid is dissolved. The difference between these two is the depression in the freezing point. Then, from the experimental studies, we can say that the depression in freezing point is directly proportional to its molarity. Molarity will be calculated by this formula, that is 1000 into W2 divided by M2 into W1. Then, and we know the expression, that is delta TF is equal to KF into M, where there is the molarity, KF is the proportionality constant, and delta TF is the depression in the freezing point. Then put this value into this equation, we will get that the delta TF is equal to KF into 1000 into W2 divided by M2 into W. And then to calculate the molar mass, M2 is equal to 1000 KF into W2 divided by delta TF into W. This is the mathematical expression or the relation between the molar mass of the solute and the freezing point of the equation. Okay, thank you. We'll see in the next video.